Okay, so yeah, we'll get started. I think more people will show up over time, but I think now's a good time to get started. So yeah, welcome everyone to this Teach PhD workshop. I'm Jonathan Scarlett, Assistant Professor in Computer Science and Mathematics, and one of the members of the IDS organization team. So just briefly about IDS, we're a very interdisciplinary institute in the US, combining researchers from computer science, maths, engineering, and other areas, all relating to the common theme of data science. We also have partnerships with agencies and industries throughout Singapore. And some of our current main projects include Grab NUS AI Lab, I say projects and sort of teams, Grab NUS AI Lab and AI in Healthcare Grand Challenge. So one of the things we do is have a PhD program, which we've been admitting students over the past few years. And just last year, we started doing these workshops for students to be able to present what they've learned in their first couple of years of PhD. And yeah, it's for the benefit of both our students and the attendees. So it gives our students a chance to get some sort of teaching experience and yeah, be able to present what they've learned and also maybe build their knowledge by preparing. And also, of course, we want it to be useful for the attendees so that they can learn perhaps a less familiar topic. And of course, we'd encourage interactions and yeah, we hope that this can help sort of share the knowledge that our students have accumulated. So yeah, I think I won't have much else to say, so it's all in Zexu's hands from now on. His topic is speech processing with deep learning, and I think we can go ahead.
Okay, thank you, Prof. Here's just a little bit about myself. My name is Zexu, and I'm a second-year PhD, entering my third year in August. And my research interest is multimodal target speaker extraction, which belongs to speech front-end processing. My supervisor is Professor Li Haizhou from Electrical and Computer Engineering in AUS. Yeah, actually I was planning to start this Zoom pool at the beginning to know more about you and also to let everybody to get familiar with the Zoom pool function. But even though we don't have much people here, we can give it a try. Yeah, and let me start this pool. I'm not sure. I think you should be able to see the questions right now. Okay, I think more or less like everybody has responded. I'll just end the poll and see if we can share the results to all of you. Were you able to see the results? It seems that we have 2 computing students and 2 engineering students. Okay. So this is the agenda of today. We have morning session and afternoon session. Ideally, each will be 2 and 3 hours to 3 hours. And each peak session, like morning session, is divided into 2 subsessions, session 1, 2, also 3 and 4. In session 1, I'll be giving an introduction to the speech processing and also the cocktail party problem. The cocktail party problem is one of the problems in speech processing. And after I give the introduction, I'll talk about some basics of the cocktail party problem. That includes maybe the performance assessment of how to evaluate the algorithms you design for the cocktail party problem, and also maybe some basics of deep learning that are currently used to design the algorithms, such as the neural networks, training paradigms, data sets. There are 2 research directions to solve the cocktail party problem. namely the speech separation and also the speaker extraction. So speech separation is more or less like source separation problem, which given a speech mixture of two or more speakers speaking at the same time, the task is to divide the speech mixture into a set of individual streams, where each stream only contains a single speaker's voice. And speaker extraction, on the other hand, is quite different. Given maybe two speakers in the mixture, we are only interested in one speaker in the mixture that we call the target speaker. And we only try to estimate the target speaker's clean speech in the mixture. And how we define the target speaker may be in many ways, such as we extract the male's voice, or extract somebody we already know, or somebody whose visual reference is given, we want to extract his voice. So this is the agenda. The objective of today is just to gain exposure of speech processing and its applications. And we want to learn some deep learning approach for cocktail party problem, and also maybe to relate to your own research and get inspired. And lastly, just to make friends and have fun. If you have any questions during this session, you can just interrupt me anytime. Or if you feel comfortable typing in the chatbot, I'll reply as soon as possible when I notice it. Now we'll jump to session 1. In session 1, this is the outline. Session 1 is about introduction to speech processing and the cocktail party problem. So in session 1, first we'll be talking about human language processing, mainly the speech and text processing. And also I'll let you know about the real-world audio, how we process the real-world audio, like the waveforms format and the spectrogram format, and maybe the short time Fourier transform, which is a popular tool in signal processing, speech processing. After that, I'll introduce you the cocktail party problem, including the definition and its applications. So human language processing is popular. Like many big companies have projects on this language processing. For example, the famous Google Duplex 2018. So it is a technology, not sure whether you have heard of it, but it's a technology powering a new Google Assistant feature, which it builds as a completely automated system. And Google Duplex can essentially make phone calls for you, but with a natural sounding human voice instead of a robotic voice. And here's a demo of this Google Duplex. So in this demo, you're going to see that the Google Assistant will help you ring up a salon or a restaurant to make an appointment for you. And you don't have to call yourself. You don't have to make the phone calls by yourself, even if the restaurant doesn't have an online reservation system. So I'll play the video right now. If you cannot hear the sound, just let me know. Otherwise, I assume you can hear it.
The progress with the assistant. As I said earlier, our vision for our assistant is to help you get things done. It turns out a big part of getting things done is making a phone call. You may want to get an oil change schedule, maybe call a plumber in the middle of the week, or even schedule a haircut appointment. You know, we are working hard to help users through those moments. We want to connect users to businesses in a good way. Businesses actually rely a lot on this, but even in the US, 60% of small businesses don't have an online booking system set up. We think AI can help with this problem. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut for now. Okay, we have a 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks. Great. Have a great day. Bye.
That was a real call you just heard. The amazing thing is the assistant can actually understand the nuances of conversation. We've been working on this technology for many years. It's called Google Duplex. It brings together all our investments over the years in natural language understanding, deep learning, text-to-speech. By the way, when we are done, the assistant can give you a confirmation notification saying your appointment has been taken care of. Let me give you another example. Let's say you want to call a restaurant, but maybe it's a small restaurant which is not easily available to book online. The call actually goes a bit differently than expected. So take a listen.
See how may I hear you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people? When? Today?
Next Wednesday at 6 p.m.
Oh, actually we leave here for like upper 5 people. For 4 people you can come.
How long is the wait usually to be seated?
For when, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Yep. Bye bye.
Again, that was a real call. We have many of these examples where the calls quite don't go as expected, but the assistant understands the context, the nuance. It knew to ask for wait times in this case and handle the interaction gracefully. Look,
whether you're building dynamic network models or forecasting real-world behavior.
Well, I think it's good enough now. I think you know what it is talking about. Yeah. So you can see that Google Duplex can produce a natural human voice, really like a human, not like a machine. And in this IBM Project Debater 2019, IBM built this thing. It's the first AI system that can debate humans on complex topics. And the goal is to help people build persuasive arguments and also to make well-informed decisions. Next is also a Zoom pool, which I'll start it now. I mean, you can have a guess how many languages are there in the world right now. Yeah, I assume we only have 4 people and all has responded. Or 5. Oh, actually, there are the answer is C. There are about 7,000 languages in the world. And actually, yeah, only 1 person make it correct, guess. And next is do you know how many languages have the written form? It's just instead of the just speaking only. Number 4. Yeah. Just make a guess. You don't need to search Google. Okay. Share results. More people choose only 19%. Actually, there are 56% of languages that have the written form. But only even if the languages have the written form, some people, like if it's a very less known languages, maybe in Africa, even if there is a written form of the language, the people who speak that languages might not even know the written form of the language, because what they usually do is just to communicate with each other verbally. Yeah. And now, how many languages are now endangered? Endangered here means often with less than 1,000 speakers remaining. And I'll launch the poll. Well, actually, there are 40% of languages are now endangered. That's considered quite a lot. Next, this question is about how many languages are there in the world that accounts for more than half of the world's population. What this means is that how many languages are half of the population speaking? If you get this, if you get what I mean. So I'll launch this poll. This is the last question. Well done. Like all of you have the correct answer. It's actually 23. Yeah. So like natural language can be text or speech. And when we are talking about text, in deep learning, we are usually referring to natural language processing. However, only 56% of the languages have the written form. And like I said, we don't always know if there's an existing writing system widely used. So we not only need to process the text, we also need to process the speech. So the speech processing comes in. And speech processing is not only about speech recognition. I know that speech recognition is very well known, but speech processing is divided into 3 big categories. Maybe we have the speech to text processing. We have the speech to text, maybe is the famous speech recognition. And we also have the text to speech category, where we have the speech synthesis, like Google Duplex, which can produce a natural human voice. And we may also have the speech to speech processing, which we will introduce later. Since all of us are from computer science or engineering, I guess most of you are familiar with one of the categories here. And I just want to know that which one of the following have you ever heard in speech processing? So this is pool, bunch pool. So you can tick if you have heard of it. Yeah, it seems that we have a person from speech area, like who tick every one of it. Yeah, yeah, like you know, most of the people choose speech recognition here. But after today's session, you will know more about speech processing. So this is a diagram for all the speech processing or human language processing models. We have the human on the left, we have the computer on the right. So the interaction between human and robot are divided into 4 aspects. And the first is hear the speech. That means we are representing the computer or the robots. We must be able to hear the human. And for example, like the Amazon Alexa or Apple Siri we are using, they are actually hearing our speech such that to interpret our intention or what we means. And computer must also able to read the text written by the human because sometimes the communication might not be verbal. For example, if you are shopping on Lazada, Amazon, or Alibaba, sometimes when you are trying to talk with the seller, you are actually talking with a chatbot. So it's the chatbot that is replying the text to you. Just for your information, what the chatbot is. A chatbot is an artificial intelligence software that can simulate a conversation or a chat with a user in natural language through messaging applications, website, or other things. So the text chatbot must be able to read your text such that to reply to you. And we also have from the computer to human, we have to generate the text. That's also relating to the chatbot. The chatbot is writing text to reply to you. And if the communication is verbal, like you are interacting with real robots, the robots needs to speak out the text that sounds like a person, like Duplex, that is natural and fluent. So human-computer interaction is a hot topic. We rely more and more on robotics. And one of the key aspects between human-computer interaction is this human language processing. So human language processing, most of the applications or models can be described by the following 6 models. In these slides, the black and blue, what we call this is a waveform, and we use it to represent the speech. And you can see a paper here, we use it to represent the text. So human language processing can be here summarized into the following categories: from speech to text. Model is you can treat it as an algorithm to transform the input to the output. And we have the speech to text, text to speech, speech to speech, and also text to text. That's more related to natural language processing. We have the speech to class, like recognizing the emotions or something. We have the text to classes. So we will look into these 6 models one by one, and I'll introduce you the models related to speech processing. The first model is from speech to text. That's commonly known as speech recognition. And actually in speech processing, we not only call it speech recognition, we call it automatic speech recognition, in short, like ASR. And this model, or we call this algorithm, is a traditional speech recognition algorithm where you can see it's quite complex. It actually consists of 3 modules. The first module is front-end signal processing. We also have an acoustic model here. We also have a language model here. The input to the model, or we call it the algorithm, is a waveform that is usually recorded by a microphone. And the output is just a sentence we recognize. I'll briefly talk about the three modules. The front-end signal processing module is to transform the speech waveform into some intermediate feature representations. For example, in this traditional ASR, I think it's more like a short time Fourier transform, which we will talk about this later. It's a signal processing tool, which is very widely used in our community. And we also have the acoustic model here. So the acoustic model will help to map these feature representations into some recognized lexicons. Lexicon is an alphabetical list of the words in the language or the words associated with particular subjects. You can treat it like words. And after that, we have the language model to connect all the lexicons, or maybe we call the words, into a complete sentence. So this is the whole pipeline. It's quite big. This model usually maybe 2 gigabytes. So it's difficult to put it in a cell phone or some online devices. So with deep learning, people have transformed these automatic speech recognition algorithms. And in 2019, Google has come up with a end-to-end algorithm or end-to-end model to transform the speech waveform into text. End-to-end just learning in this context, in the context of AI and machine learning, means that it is a technique where the model learns all the steps between the initial input, that is the speech waveform, and the final output, the sentences, in one whole module. And this is a deep learning process where all different parts are simultaneously trained instead of sequentially. So previously, we can see that we have 3 sub-modules that are quite independent of each other, but now it's just combined into one whole module. We just need to input the speech, and the model will output the text. In this is a demo over here. On the left side is a traditional one, which is the model is quite big. It's got and we need to do server-side transcription. That means whatever you speak to your phone, the phone will transfer your speech to their server, maybe located in some countries, and then they will process the speech waveform into sentence on the server and then transform back to you on the phone. So this process is quite slow. However, with the end-to-end model, we are able to do on-device transcription, which is much faster compared to the server-side transcription. Like you can see the comparison between the two. Yeah, so the difference is quite obvious. And now after speech to text, I'll briefly introduce text to speech. That is usually maybe text to speech synthesis in speech processing. So here is about speech processing, speech synthesis. Speech synthesis is the artificial production of human speech. We're given a text. We want the computer to generate the speech with different properties, maybe like speaker identity or some other things. So this is a model called WaveNet. It's a speech synthesis model produced by DeepMind. And this is first maybe you hear about the speech synthesized by this model. This model can generate speech with a different speaker identity given the same text input.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
It's a male voice.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
I guess you can hear the sound. As you can see, as you can hear, it can generate the speech from like sounds like different speakers. However, this model to generate speakers is mostly speaker dependent. That means when you are doing training on a data set, when you train on the female voice, you are outputting a female voice. So you cannot anyhow generate a speaker's voice, most likely. And now it also can generate different languages.
第一班商业航班在1919年来往于美国和加拿大。
So this is actually speaking Chinese. And also given different text input, it can speak out the different text. So the content is different. Also this thing.
The to now also very good. Sugar acid, seed cells, behaves. The lambu. He has the head chain with going to 50 levels of power.
And they can also generate music. Yeah, so this is speech synthesis. Now we also we have speech to text, we have text to speech, and we also have speech to speech models, which is what my research is focusing on. So one common application we can think of belonging to speech category is speech enhancement. So speech enhancement basically is to denoise the noisy and reverberated speech into a clean speech. Like you can hear the input to the algorithm is like this.
Slide the tray across the glass top.
Here again.
Slide the tray across the glass top.
You can hear it's very noisy and you can hardly understand what is saying inside. It is even hard for us to understand the noisy speech, not to mention to let computer to do speech recognition on this. So now we need some speech enhancement algorithms to try to denoise it. We have the output clean speech.
Slide the tray across the glass top. Slide the tray across the glass top.
So I think it's much clearer to understand. Maybe we hear again the noisy.
Slide the tray across the glass top. Slide the tray across the glass top.
Yeah, so this is speech enhancement. And this speech enhancement can be seen as a front-end pre-processing step for other speech processing, such as speech recognition. Yeah, actually, Zoom has an internal speech enhancement algorithms and noise reduction function. I'm not sure whether you have noticed it. And if you have noticed it, are you satisfied with it? I'm going to launch this poll number 9 to see whether you are satisfied with it. You should be able to see the post right now. Actually, it seems that most of the people here are satisfied with it. I am actually also somehow quite satisfied, but there are also situations where I find it not useful because, for example, if you suddenly close a door, or if there are other people around you who is also speaking, actually all these noises will be recorded by Zoom. And yeah, I found it quite annoying sometimes. So in speech processing, we not only have the speech enhancement, we also have speech separation problem, or the speaker extraction problem, which is all belonging to the cocktail party problem, in which the cocktail party problem is that sometimes the noise is not only environmental noise. The noise can be other people's speech, like a two-speaker mixture in this case. And this is very, the reason why they call cocktail party problem is that this usually happens in a cocktail party while you are talking to your friends. There are other people speaking around you, so you only want to hear a speech one by one, not the speech mixtures. So this speech separation aims to separate these two speakers mixture into individual streams. The two speaker mixture is like this.
The solution requires development of the human capacity for social interest.
So it's two people speaking at the same time. We hear again.
The solution requires development of the human capacity for social interest.
So speech separation algorithms can help disentangle the speech mixture into different streams.
The solution requires development of the human capacity for social interest.
Earnings were helped by lower tax rates and by engineering and...
Yeah, so this is speech separation. In speech processing, we not only have the front-end processing, like enhancement and separation, we also have this voice conversion. It's if you have watched this, watched Conan's bow tie, it can transform the voice. So this is what this task is about. So voice conversion is a technology that modifies the source speaker's Conan's voice and make their speech sounds like another reference speaker's voice. So in this case, the source speaker is a female, and we want to transform her speech into a speech that sounds like another person. For example, if this source speaker is female, we can hear her speech.
Please call Stella.
And we want to transform her voice like this person's speech.
Ask her to bring these things with her from the store.
So given this reference, this is the output.
Please call Stella.
So we hear again.
Please call Stella.
Please call Stella.
And the reference.
Ask her to bring these things with her from the store.
As you can see that these two really sounds like each other. And it can also transform into a female that sounds differently, like the source female.
Please call Stella. Ask her to bring these things with her from the store. Please call Stella.
We hear again.
Please call Stella.
Please call Stella.
Ask her to bring these things with her from the store.
And for female speakers, they do not sound very good. And hopefully we can see a model that can perform as good as Conan's prototype very soon.
Please call Stella.
Okay, so we have speech to text, text to speech, and speech to speech. We also have text to text in human language processing, where we have different applications like the translation, like translating English to Chinese, or we have summarization, summarize one paragraph into one article into a paragraph, or we have the chatbots mentioned during the online shopping platform. You input a question, you answer with something. We also have question answering. And these are actually belonging to natural language processing, NLP, but our focus today will be on speech. So text-related research will be less focused today. Here is also the text processing, text to a class, maybe like a sentiment analysis or emotion classification. And we also have the speech to class, directly process the speech into a class, like emotion recognition or sentiment analysis from speech. And we also have the acoustic event analysis, acoustic scene analysis, or from cough to COVID detection recently. So the text to class, more detailedly, we'll introduce it in more details. The first is the very traditional task and also very useful. It's speaker recognition. It's more or less like face recognition, where I think you have heard about. So speech recognition is given a input speech waveform. We want to recognize which of the speakers in the database to this speaker belongs. And if you have noticed that when you call Hey Siri, when you're using iPhone, my Siri responded to me. Actually, Siri only tries to recognize your voice and responds only to you. When other people call Hey Siri to your phone, most likely the Siri do not respond. Although this is sometimes not accurate. Yeah, but it has the speaker recognition model built in. And in audio, in speech to class big category, we also have the keyword spotting. Keyword spotting is given an input speech, we want to know whether this speech is a keyword. For example, you only call Hey Siri and then Siri responds. So this is like Amazon Alexa or Siri. They have an inbuilt keyword spotting system to detect the Hey Siri you are trying to say. And they only fully listen to you after they hear the Hey Siri command. This is to save energy or prevent any misinterpretation. My Siri keeps responding to me. Okay, so in speech to class, we also have the sound event classification. Input audio. We want to recognize whether this is a guitar sound, a car sound, or speech, or is dog barking. We also have the acoustic scene analysis. The difference between scene and event is that an acoustic scene is formed with multiple sound events. For example, in an airport, it's actually formed by flight announcement, maybe also the luggage dragging, people walking. And the acoustic scene classification, their accuracy right now is quite low, like 60%. So there is still much room to improve. The focus today will be speech-to-speech and more detailed the cocktail party problem in speech enhancement. Yeah, like we have heard about. So this is the section 1. We have finished the human language processing. We will talk about this in the later. Now maybe we have a 10 minutes break. So I'll see you at 10 o'clock. Hello, welcome back. So we have talked about human language processing, speech and text. And in this short session, we are going to talk about the real-world audio. And that includes the waveform and spectrogram format, and also the short-time Fourier transform processing. Real-world audio. To understand the acoustic environments in our daily life, also with our auditory system, we need to understand certain problems like what and where. What means that if it's an audio, what is it a speech, music, or car pass by? Or if it is speech, is it conveying any message? Or from the speech, you can roughly know about the information about the speaker, such as his age, gender, or the linguistic origin, or maybe the mood he's having. And also you can also know where the sound comes from. Is it come from the up, down, left, right, or you can even get a sense about how close the sound source is near to you. So the real-world audio has some channel characteristics, whether it's a direct signal from you hear from the person speak, or it is a speaker playback. And from the environment, it might also have some additive noise from other sound sources, or the reverberation from any surface reflections. The audio can be single channel or multi-channel. Single channel actually means that it is recorded by a single microphone. And when you are playing back the single channel audio, even if you direct to two speakers, they're actually playing the same thing. The audio can also be multi-channel, where it is recorded by a microphone array. So a multi-channel audio, depending on the time of arrival from the sound source to the microphones. This is actually a lot of microphones in the surrounding. We can make use of the special features of the audio. And actually when you are playing back the multi-channel audio, such as the stereo audio is 2-channel. From left and right, they're actually different waveforms. And today we will be focusing on single channel here, which the sound is recorded by a single microphone. Audio waveform example in this slide. Speech signals are actually sound signals. So sound signal from high school physics, it is actually defined as pressure variations traveling through the air. These variations in pressure can be described as waves, and correspondingly, they are often called sound waves. In the current context, we are primarily interested in analysis and processing of such waveforms in a digital system because they are recorded in a microphone. There will therefore always assume that the speech signals have been captured and converted to a digital form. And the digital form is actually represented by a sequence of numbers xn, which represents the relative air pressure at time variation Tn. And this representation is commonly known as the postcode modulation, or PCM in short. This is the waveform, and you can have a closer look at the waveform. So it is actually a point at a time. Usually the speech or audio waveform, we process it as a 16 kilohertz for speech That means 1 second of speech has 16,000 points, like here. And each point, if it's represented by integer 16, each point has 256 possible values. And yeah, so here we have ABCD 4 waveforms, all are saying some frames or words. Maybe you can have a guess which one of the waveform is actually speaking a different thing compared to the others. You have ABCD, all the same and all the different. I'm going to launch the poll. Okay. 2% choose B. I think maybe because the sharp sound happened over here. And 1 people choose D. And the correct answer is all of them are the same. All are speaking the same thing. It's a Chinese word, 你好, means hello. Actually, no one can say exactly the same thing twice. So even if you say the word 你好, it's actually the waveform is different every time you say it. Just like the old saying, no man ever stepped into the same river twice, for it's not the same river and it's not the same man, and same as the speech. When we are talking about speech processing, we sometimes divide into 2 categories. We can talk about the time domain speech processing, or we call it the frequency domain speech processing. And also we usually see the speech or audio in the following 2 formats: time domain format and frequency domain format. And just now we've introduced the time domain format, which is just the raw representation of the air pressure. And in speech community, we often call this speech waveform samples because it's sample at times. And the models who directly process these time domain speech samples are usually referred to as time domain approach. And we also commonly see the following representation of audio and speech, which is spectrogram, formerly time frequency representation. And this representation is obtained by applying short time Fourier transform to these waveform samples. So they are actually the same thing. And each point in this time frequency represents a value, and this value is represented by a different color, you can see. Short time Fourier transform, which transform this one into this one, is a well-known signal processing equation. And this started from the discrete Fourier transform. The Fourier transform maps a length. In practice, we work with the discrete time signals, which we introduced earlier. And this equation, you don't need to know by the end. You don't need to understand it for today. I just introduce it to you. And this equation maps a length of n speech signals into a complex value frequency domain representation. This complex value because it has magnitude and phase part. Short time Fourier transform is different from discrete Fourier transform. The difference why we do not use discrete Fourier transform is that speech signals are non-stationary signals. If we map a length of n signals, I mean the overall length of n signals into a complex value, it's just going to be a one vertical line in this spectrogram. But this is not stationary, so it's varying at different times. So if we transform the whole thing into one vertical line, it will just be a average of all things we've spoken across the maybe 3 seconds. So it does not have any meanings. So short time Fourier transform, different from discrete transform, is that short time Fourier transform only a segment of the speech into one vertical line and process segment by segment and becomes the many vertical lines. And we draw these vertical lines together, forming the time and frequency spectrogram. Because this Fourier transform has real and imaginary part, we can have the magnitude spectrum and we can have the phase spectrum representing because it is real and imaginary parts. And we can see that the magnitude spectrum, actually, we can see some parallel lines, not like phase spectrum. Like because of these parallel lines, you can see that it's much easier to understand or learn something from this magnitude spectrum. That is a pleasant domain to work with compared to a time domain. And when we are processing speech signals in the frequency domain, that means on the right side, we usually process the magnitude spectrum only because it is you can draw some conclusions from this, but phase spectrum is you cannot actually interpret much things from the phase spectrum. It's very difficult to process. And next, I'll maybe introduce more about the short time Fourier transform, how it is calculated. So the first step is called windowing, speech the signals into shorter segments. So this segment is this speech is one of the segments along the very long speech signal, which this is only a short part of this speech waveform. And we apply the window to it. This is called windowed speech segment. And this windowed speech segment is we applied a discrete Fourier transform to the window and transform it to this thing. And like we said, the phase is difficult to manipulate. Therefore, we only consider the magnitude here. And we have frequency in the horizontal axis and the value of each frequency at a vertical axis. And we can also get the power of it, which we give it a square. That is the power of discrete Fourier transform of a speech segment. However, there's a large difference in the range of the different frequencies in this plot. And due to these differences, this representation do not easily show any relevant do not easily show relevant information. Therefore, what we usually do is we apply a log to the magnitude, and we obtain a log spectrum of this speech segment, which is much more meaningful than the previous one. And this just represents a single segment. This just represents a single segment, and we have many segments along the speech, along the time. And if we want to put them in together, we just rotate this 90 degrees, make the frequency the vertical axis, and this is a single time. And we use different color to represent these values. And we draw the segments together, we have this magnitude spectrogram. And as we said, we have the linear scale, and we also track the log scale. And there's also another scale called male spectrogram in male scale. This is because studies have shown that humans do not perceive frequencies on a linear scale or log scale. We are better at detecting differences in low frequencies rather than high frequencies. For example, we can easily tell the difference between 500 Hertz and 1000 Hertz, but we can hardly differentiate 10,000 Hertz versus the 10,500 Hertz, even though the distances between the lower and upper frequency are the same. So in 1973, Stevens and some other people proposed a unit of pitch such that proposed this thing called male scale, which perform a transformation, mathematical operation from the frequency to a pitch. So here are three different spectrograms at different scale. We have the log scale, linear scale on the left. We have the log scale in the middle, and we have the male scale on the right. Male scale is more simulating humans' auditory system. Actually, for computers, the log scale is the most common visualization of the speech, which is given in decibels. And this is useful and much easier to interpret and oftenly used. And in this thing you can see is saying pure pleasure. Here I will give a Python demo on how to transform the speech waveform into this spectrogram representation, which all the materials are here and the demos are here. I will put the links into the chatbot. You can try it, and I'll also explain what it is. I'll type in the chatbot. So this is a collab demo over here. Neural audio is a popular signal processing tool to process the audio. So we first install the package. We run the code one by one. Yeah. So this is the installation of the neural audio package. Sharing access. what does it mean? Sorry. Or is it you can share. Only change to enlarge the link. Is this the link? BS. I guess this is the link right now. You can try. Okay, sorry. Okay, so we load the spectrogram function from the neural audio package, and also we use the SciencePy to some functions loading over here. We run this thing. And in this session, just let me. Okay, I'll explain this line by line. First, I link this code to my Google Drive such that to import any audio samples. So the path is my audio samples, and Librosa is a package to load the speech waveforms into X here, which are the audio path plus the audio name. SR is the sampling rate, which is 16 kilohertz as set here. Mono means that we choose it to be a single channel audio. So there are several audios in the Google Drive, which consists of pure tone wave, WAV. WAV is the audio format. We have the music, we have a clean speech, and we have a noisy and reverberated speech. And this X is actually the audio we've loaded, and we convert the X into a torch tensor, PyTorch. After that, we have imported the spectrogram function from the neural audio. We can just use this function to transform the speech waveform into the spectrogram linearly, the magnitude spectrogram. And also we have the log representation and the mel representation. Then to visualize the spectrogram, we use the Python plot, which is over here. And this is actually a pure tone spectrogram. I'll play the different audios to let you have a sense what it is. So pure tone is Yep, so this is the pure tone, different frequencies at different time. We also have the music. You can hear the music first. Music is not pure tone anymore. It consists of multiple tones, which if we put music here, you can see how the spectrogram looks like. Yeah, so each consists of multiple tones instead of the single one just now. We also have clean speech and noisy speech. Clean speech is this.
Slide the tray across the glass top. Slide the tray across the glass top.
Noisy speech.
Slide the tray across the glass top. Slide the tray across the glass top.
So if we visualize the speech, clean speech, this is the spectrogram. If we see the noisy speech, it's quite different from previously. I think I've shared the link in the chat. You can have a try. You can have a try now. If you have any difficulties, you can discuss with me. Yeah, so I just pause here, or you can have a try. Maybe 10 minutes. And we'll resume the presentation at 10:40. Hi, hello. It's 10:40. If you have any further questions about the code, you can talk to me later and we will solve it. Now I'll continue the presentation. We've talked about speech and text. We've talked about Fourier transform. Now I will introduce to you the cocktail party problem, its definition and applications. Cocktail party problem. One of our most important faculties is our ability to listen to and follow one speaker in the presence of others. And this is such a common experience that we humans have for granted, but not for machines. We may call it the cocktail party problem, which is to emulate such ability in machines to do that. So for short, human can focus on the voice produced by a single speaker in a crowded and noisy environments, include the noise, bass noise, or other person's speech. We can only focus on this person. And there's a little bit difference between speech enhancement and the cocktail party problem. The speech enhancement actually is a speech and non-speech separation, which usually called denoising, which there's only one person speaking and there are some surrounding noises. We want to get the clean speech. Whereas for cocktail party problem, there are multiple speakers speaking, and we want to know each of the clean speech from the other speakers. Why do we need to study the cocktail party problem? This is because in human-machine interaction, speech is vulnerable to be corrupted by the sound within the experiments, within the environments, and speech perception, such as speech recognition, their performances degrade significantly in the presence of noises, especially the interference speaker's speech. How to come up with a solution to make human-machine interaction robust against these adverse environments is still a challenging problem. To solve the cocktail party problem, there are two solutions, like we mentioned: speech separation and speaker extraction. Speech separation, as illustrated on the right, they separate every speaker out from the mixture into individual streams. And speaker extraction only focus on a single speaker of interest and extract only the target interest speaker's speech. In this case, is the yellow speaker, the blue speaker. And we need for speaker extraction, we need an auxiliary reference to determine who is the target speaker in this mixture we want to extract. This can be the target speaker's voice, signature, or something else. The applications of the speaker extraction. First is the noise reduction category, where in the conference systems, such as Zoom, they can help suppress the background noise or other people's speech. It can also help in the hearing devices, hearing aid devices, or live recording or post-production. And that's for noise reduction direct usage. For the downstream tasks, such as it can be used for some smart assistance of the robots to build a robust automatic speech and speaker recognition system during human-robot interaction. Also, it can also help in the audio information retrieval because all these things need the speech and speaker recognition. Yeah, so by now we've finished session 1. We will start in the session 2. There was a break between session 1 and session 2, but since we had a 10 minutes break during the coding session, so we can just start the session 2. In session 2, we talk about some basics of the cocktail party problem that includes the performance assessment of the algorithms that solves the cocktail party problem. Also, we'll talk about some basics of deep learning. Depending on the time, I'll decide like which of the following we will focus on. So in performance assessment, they are divided into mainly 2 categories: the subjective evaluation and instrumental evaluation. And also there are some other things, but not very advanced. So subjective evaluation basically is human give a score manually by listening to the speech samples produced. The instrumental evaluation is that there's an algorithm to give the score automatically by listening to the speech samples. And in each of the evaluation, there are 2 things to evaluate, basically the speech intelligibility and speech quality. Speech intelligibility, in short, SI, is defined as how clearly a person speaks so that his voice or her speech is comprehensive to a listener. It's like how much we can understand the speech. Speech quality is the quality of speech, like such as against the distortions or any other things. So we'll first look into the subjective evaluation into speech intelligibility. Subjective speech intelligibility evaluation, there are mainly 3 tests. We will first into the psychometric function. Psychometric function is basically have several sub-methods, but the main idea is that given the SNR of the speech input, SNR is defined as the signal-to-noise ratio. So the larger the SNR, the clearer the speech. The lower the SNR, what you can hear is just the noise. So as you can see, as the SNR, signal-to-noise ratio, increases, like we can understand more and more of the speech. Percentage correct means the percentage of the content or the words we understand from the speech. So it's this relationship. And previously it's just a drawing. It's not from real experiments. And this one is from the real experiments. Percentage correctness response versus the signal-to-noise ratio. This is an experiment conducted in 1998 and 1997. And this is an intelligibility score obtained by 18 subjects in the identification of 18 stimuli. So stimuli might be, in this case, the words to understand. And they are as a function of the acoustic degradation or the signal-to-noise ratio. As you can see, the blue line is purely the speech you can hear. The trend is that with the higher the signal-to-noise ratio, the better you can understand the speech. And the blue line, the black line is with a lip. If you observe the lips while hearing the speech, the intelligibility increases. And this is a face 3D model over here. If you can see the face 3D model improves us. And of course, if you can see the real person's face, it is the best. So within the psychometric functions, there are several methods to determine what's the intelligibility of the speech. The first one way to evaluate one method is to sampling at the predefined SNR. For example, what is the percentage correctness of the speech at a defined signal-to-noise ratio? So to compare across various intelligibility of speech, where we want the SNR to be, we fix an SNR, for example, we fix an SNR to be 13, and we compare the percentage correctness across various speech. This is sampling at a predefined SNR. And also we can sample at a SRTX. So SRTX means that it's an SNR at which a test subject achieves a X percentage correctness. A commonly used one is a XRT50, where that we want every test sample to have the 50% correctness of the interpretation, and we want to know what's the signal-to-noise ratio of the input speech. And from this figure, you know that to interpret, you can see at an XRT50 over here, what's the signal-to-noise ratio of various inputs that can be understood. The rectangle is a complex tone. Complex tone is like I've played the audio sample before. You can get a sense of it. And you have the broadband noise. It's just a noise. And you have 1 speaker speaking, 2 speakers speaking, and 8 speakers speaking. And in this figure, you can see at SRT50, there are actually a large difference of the signal-to-noise ratio in between for this speech perception threshold. And to explain more detailedly for complex tone over here, even if the signal-to-noise ratio is as low as 24, you can understand the tone by 50% chance. However, for 2 speakers speaking at the same time, the solid circle over here, you need the SNR to be like almost 0, such as to understand the 50% of the speech the person is saying. And here we are doing a test where you can vote the SNR that you feel you roughly understand what the female speaker is speaking. This is not this is roughly to let you have a sense of the SNR50 test. Let's say you understand 50% of the speech what is talking about. You vote which one you understand about 50% of the female person speaking. Yeah. So if the signal-to-noise ratio between the female speaker and the male speaker is minus 40 dB.
Place blue in Z2 soon. Place blue in Z2 soon.
I think most people couldn't hear the female speaker speaking. Yeah, I'll launch the pool first, then to let you hear. Okay, now we hear this one.
Place blue in Z2 soon. 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 Place blue in Z2 soon.
So the undistorted female speaker is here.
Bin blue at 08 soon.
Yeah.
Place blue in Z2 soon.
Okay, I'll end the poll. I assume you have heard it. I think you can see the statistics. More of us can hear better when it's much clearer, like around -5 to 0 dB. This also aligns with the here, right? When there are two persons speaking, the solid circle dot is around between -6 to 0 dB. Yeah, this is the SRT50 test.
Place blue in Z2 soon.
Okay, so beyond the previous intelligibility test, we also have another test called Diagnostic rhyme test for intelligibility. So given a pair of words that sounds similar, like will and feel, the people will listen to the speech and choose one of the following he felt that he hear. And also there could be a metric test for intelligibility where the people choose the words that he can hear in the list of words, so-called a matrix. For example, the speech might be saying 5 words containing the name, verb, something like this. Michael get 12 red houses, and the listener will choose from the matrix of words to select the words. And if it's audiovisual evaluation, the video of the person, like the face of the speaking person, might be available. Like a setup for audiovisual speech intelligibility test. Like this is the metric test where you watch the people speaking and you select from the color, you select from the digits. That's the subjective evaluation where human give a score by listening to some samples. Now we look into the speech quality. Speech quality, there are mainly 2 ways in subjective speech quality analysis: the mean opinion score or the multi-stimulus test with hidden reference and anchor. So the is the most widely used test in speech processing. And also when you publish papers, most of the people choose to use this. Mean opinion score is an absolute category rating where you rate the quality of the speech you hear on a 5-point absolute category scale, like from 5 to 1. And finally, it's an average across all listeners. When you do this test, by right, you should hire volunteers from the online. and the average results should be reported. And also beyond MOS, we have a multi-stimulus test with hidden reference and anchor, where that the scale is absolute scale from 0 to 100, similar to the previous one. The difference lies between that the previous MOS, you only hear the speech samples to be evaluated. However, for this test, you have multiple speech to listen to and to score it. First is the unhidden reference, which is the clean reference, undistorted reference. And you also have a unhidden reference, which serves as an upper bound quality and also to validate the subject's performance in case he anyhow like rate the thing. Also, we have an anchor signal, which serves as a lower bound quality and to fix the dynamic range of the test. And of course, we have the signal and the test, which is the main thing we look for. And yeah, we listen to this speech and we rate accordingly. And sometimes we loop these signals and signals switch between signals to allow easier comparison. And this is a screenshot of the test subjects doing audiovisual evaluation using this test. Like, not sure whether you can see this is the scale and this is the several sound. Yeah. So we've done the subjective evaluation. Now we look into the instrumental evaluation. Instrumental evaluation, the motivation is that the subjective evaluation are expensive. It requires time, requires test persons and also equipment. And the basic idea for instrumental evaluation is to build an algorithm which to predict the outcome of the listening test. And this does not require the test subjects, does not require any equipment, and we can immediately get the answer and reproducible. But this instrumental test is only an estimate of the truth. So the instrumental also is divided into speech intelligibility and speech quality. The speech intelligibility, the well-known one to use is STOI. It stands for short time objective intelligibility. So the estimated SI index, SI is the speech intelligibility based on time-aligned, clean reference, and the signal and the test. So it essentially computes the average correlation between the short time temporal envelope of the reference signal and the test. So the input to the algorithm is the clean speech and also the speech and the test, and you output the score. It has useful predictions in various conditions, including noisy speech processed by single channel noise reduction algorithms and some other things. And it can be applied to speech in various languages, not only English. It is language dependent. And there's an extended STOI, stands for ESTOI, which is robust to fluctuating massacres. All these algorithms can be obtained online, that they are already written in the package. You can use it. So there are also other methods to predict the speech intelligibility, and in recent years, this is a research trend. It's a research direction. There are many different people propose different methods. Yeah. So there's speech intelligibility. And another main criteria is speech quality. So for speech quality, the motivation is the same for to save time, people, and resources. To build, and basic idea is to build algorithms to predict the outcome of listening tests. And algorithms for speech quality estimation are quite a lot. And existing algorithms range from waveform distortion measures to algorithms inspired by the models of the human auditory system. Like, you can read the references if you want to know more about the details. And depending on the information that is made available to the algorithm, a voice quality test can be divided into two main categories. A full reference algorithm, which access to the original clean signal and the signal under test. A no reference algorithm just evaluated the signal under test. So PESQ is the very famous evaluation algorithm to evaluate the speech quality. It is originally a family of standards comprising a test methodology for automated assessment of the speech quality as experienced by a user of a telephony system. And it is a full reference algorithm. That means it needs to compare between the clean speech and the signal under test. PESQ results principally model the mean opinion scores, which was the subjective evaluation that covers scale from 1 to 5, that bad to excellent. And beyond the PESQ, we also have the waveform measures. Let S denote the clean reference signal, and let S hat denote the time-aligned process signal, which is the signal under test. And one very commonly used waveform measure is the signal-to-noise ratio, or segmental signal-to-noise ratio, where the equation is over here. It's on log scale. The energy of the signal versus the energy of the noise. The noise is just the clean signal minus the estimated signal. It's in decibel scales. Yeah, this is the pictorial illustration of signal-to-noise ratio. We have the output from the model. We have the ground truth. We have the signal-to-noise ratio is the ground truth divided by the differences in between. However, this signal-to-noise ratio has one disadvantage. That is, when we are calculating the difference, which is E, this yellow is the output of the model, blue is the ground truth. If the yellow is in this direction, and if we simply larger the output of the model, which is a signal under test, you can see the error actually decreases, which is not a good thing to expect. Therefore, people have come up with a scale invariant signal-to-noise ratio. So there's a SI in front, prefix in front, where in this picture, we only want to know, we want the parallel components of the estimated signal to be as large as possible, while the vertical components of the estimated signal to be as small as possible. This is the motivation of scale invariant signal-to-noise ratio. So we commonly use the SI-SNR and SI-SDR interchangeably. SNR signal-to-noise ratio, SDR is signal-to-distortion ratio. They actually means the same thing. So as you see, we want the signal-to-noise ratio to the signal to noise ratio to be infinitely large when the extracted signal xt is compared with the vertical components. So in this equation, you can see that the xt divided by xt is infinitely large. However, if we simply enlarge the output of the model, this thing remains the same when we input a scaling factor. So the scale invariant signal to noise ratio is invariant to the scale of the output. On top of that, we also have the improvements on the scale invariant signal to noise ratio, where that we have the very noisy mixed audio. We have a clean audio. We have a SI-SDR. We have the extracted speech. We have the compare with the ground truth, SI-SDR number 2. And the improvements is simply the difference in between the two SI-SDR. That's the instrumental evaluation on speech intelligibility and quality. There are also other measures beyond, we might need to consider beyond the instrumental and speech intelligibility and speech quality, which that some other attributes are important. For example, the speaker identity, gender, and age of the extracted speech. We want their identity to be as similar as possible to the target ground truth, and also the emotion of the target speaker, and some other things. And in particular, there's one thing to note is that there's a listening effort, which means the amount of cognitive resources allocated by an individual to achieve a particular performance in a listening test, which is the effort we made to, such as to understand the speech produced. Yeah, that's all for the performance assessment. So we have done session 2, the performance analysis, and we've only left with the basics of deep learning part. I think the time now is 11:13. We can have a 5 minutes break or 7 minutes, or see you at 11:20. Yeah, after that, we'll go to the last part of the morning session. Hello. I'll resume now. Going to the last session in the morning, which will talk about the basics of deep learning. Yeah, previously we talked about the cocktail party problem. We talked about there are two research directions: speaker extraction and speaker separation. And all of them recently with the advance of deep learning, they have transformed the two research. And actually, deep learning is just using deep neural networks to process the S algorithms. And after the feature extraction stage, such as the short time Fourier transform, or directly input the speech signal, the processing of the signals is performed with a deep neural network. And typically, deep neural network in cocktail party problem feed-forward neural net, fully connected neural networks, the convolutional neural networks, recurrent neural networks. So deep learning is a class of machine learning methods that jointly learns multiple levels of representation and classifiers or regressors. I think we've done the survey before. More of us are from computer science or engineering, so I guess we are all familiar with the neural networks. So I'll briefly talk about the neural networks, but not go into details. So first is the feed-forward fully connected neural networks, also known as the multi-layer perceptron, consisting of multiple fully connected layers. So illustrated in the figure over right, actually X1, X2, X3, and XD are the input. In the context of speech separation, this could be a speech signal. And the output could be the Y1, Y2, Y3 are the estimated clean speech signal. The reason why they call multiple fully connected layers are that there are several layers like layer 1, layer 2, and layer 3. And all these layers are fully connected, means one point here is fully connected to every point to the next layer. So we call this one point a neuron here. On the left is the equation of the fully connected layers. Input is the xi over here, xi times the weight to get in the neuron of this one. And this one actually a summation of all the neurons with a weights. And after this summation, there's a h, which we usually call it a activation function. I'll talk about the activation function in the next slide. But this overall, this whole thing is nonlinear because of the activation function. And this network performs well by jointly learning the nonlinear feature extraction of the multiple layers and also the log linear classifier. So this is the activation function where we input a value and the output value is determined by a nonlinear function. Could be a sigmoid function or a value function. Next is the convolutional neural networks. Compared with fully connected neural networks, the CNNs exploit the data structure and it replaces the matrix multiplication with operations including convolutions and pooling. That is special for the CNNs. So convolutions leverages sparse connectivity, parameter sharing, and equivalence to translation. And pooling is a local maximization. I'll explain the convolution and pooling in the next slide. So here is the convolutional neural network. In front, the front several layers are convolutional neural networks, while back end uses a fully connected layer to determine the final output. As we've said, the CNN consists of usually consists of alternating convolutional layers, max pooling layers, like convolutional max pooling. There also are activation functions, which is ignored in this picture. So if with activation function could be convolutional max pooling activation or in sequences. So convolution actually means that given an input image like 28 times 28 in resolution, this is the image. One represents represents the black, and 0 maybe represent white. So it's a binary image, black and white image. Convolution actually means that there is a kernel. In this case, it's a 3 times 3 kernel. Each of the kernel is times the part of the image, and you get a value of it. This animation is quite fast, but hope you can understand. The kernel value is the little bottom right times 1 times 0. That's the kernel. So the value of the image times the kernel, we get the output. Or we call the convolved feature. And this convolved feature is further, after the convolutional layer has a pooling layer. If it's a max pooling, a kernel 2 by 2 will be the max value of within the 2 by 2 grid. So this 4 by 4 will become a 2 by 2. If it's average pooling, the value will be the average of the 4 values over here. That's convolutional neural networks. Next is a recurrent neural network. Different from the fully connected network and the CNN, the recurrent neural networks, RNN, can model sequential data in a natural way with no need to use delay taps to specialize data. And it can process input of any length without increasing the model size. And it considers the historical information. So the input is X, the output is Y. H is represents the, let's say, represents the recurrent neural networks, and H0 is an initial state. Every time input is input into the RNN, the hidden states output a value, and the initial states also changes based on the input. So at time t equal to 2, when the feature goes in, they output a value at t equal to 2, and the hidden state also changes. And the weights to calculate the hidden states and the output are actually shared across time. So these are actually one model. It's just that inside the model, there's a feature or there's a vector that the changes with the inputs. And it also backpropagates through time for training. There are variants of the RNN, like the gated RNNs, such as LSTM or GRU, and there are bidirectional versions like bidirectional LSTM and bidirectional GRU. So the important for deep learning for cocktail party problem is that it uses deep models instead of the knowledge-based techniques. It's possible to learn the representations of the acoustic signals and visual modalities at several levels of abstraction. Now, the visual modality here, or the multimodality here, means the use of visual signals in the cocktail party problem. Like the face can also help you to extract the speech and suppress the noise. And also it helps to flexibly combine them. like the fusion stage between the signals at either early, late, or intermediate stage. In cocktail party problem, there are also mainly three training paradigms: the supervised learning method, unsupervised, and self-supervised learning. The main differences lies in the training targets, or what we call the training labels. In supervised learning, the model has an input and label pair. For example, in cocktail party problem, in speech separation or speech enhancement, the input to the model is a noisy speech, and the model output a estimated speech, and the estimated speech is supervised by the corresponding clean label that we call the input label pairs. However, for unsupervised learning, we do not have the label. We only have the input, which we want the model to learn and to train using the inputs without manually providing a label, such as the variational encoder in reference 15 to model the clean speech. But unsupervised learning is rather rare in cocktail party problem. And another one is self-supervised learning, in which the learning models are trained with inputs and automatically generated labels. So as self-supervised learning, in short SSL, turns an unsupervised learning problem into a supervised one. Actually, most of the speech separation or speaker extraction algorithms, so-called, they are belonging to the supervised learning because they have input and label pairs, but actually they sort of belongs to the self-supervised learning because the input and output label pairs are actually automatically generated, which we'll introduce later. And yeah, next slide. So we will just say that for now, the algorithms we introduce belong to the supervised learning framework, where we have the train and label pairs. In supervised training paradigm, we have a training targets to train the neural network. Training a neural network basically involve an optimization algorithm to find a set of weights of the neural networks to best map the inputs to the outputs. And the neural network output output given the input, and this output is compared with the training targets or the labels with an objective function. The function provides a measure of the distance between the output and the training actual clean signals. The training involves the 4 stages: forward propagation, where input a noisy speech, the neural network estimate the speech. And the second stage, we will calculate the difference between the clean target with the estimated output of the neural network using an objective function, such as the mean square error. And this error is going back to the neural network. And this loss is used to update the neural network's weights. Like if I replace the input output with the spectrogram, you can see that the input to the neural network is the spectrogram feature of the mixed speech. And we have the extracted clean speech to compare with the target ground truth clean speech. Dataset has a central role in the development of deep learning based speaker extraction or speech separation models. And most of the data sets consist of clean signals of several speakers, which are then used to create synthetic mixtures with overlapping speakers and acoustic background noise. And in this slide, I'll explain why we use the supervised training paradigms, but actually it is called a self-supervised learning. It is because in this picture, we see that we need the mixture speech, we need a clean speech to train the neural network. That is called input label pairs. And the input is the mixed speech. The label is a clean speech. And the mixed speech is obtained by manually adding the two clean speech together. Because these are speech signals in time domain, they are samples. Each time has a 1 point. You can numerically add them together to form the mixed speech. So in speech separation or speaker extraction, you can simulate these synthetic mixtures as much as possible without human labeling it. So these are so-called human computer-generated labels. Even though we can simulate the mixture this way, this doesn't really represent the real-world speech mixture signals. There is a little bit mismatch, but models trained using such as synthetic mixtures, they actually perform very well in real situations. So the mismatch is very small. Yeah, I think we have done the morning session. Yeah. Do you have any questions? Like if you have any questions, you can post in the chat, or you can ask me later. I think I'll put my email in the chat box in case. The afternoon session start at 1 o'clock. 1 p.m. sharp. Yeah. Like you can, yeah. If there's no questions, see you in the afternoon. Thank you for your attention.